Okay, so let's try this problem. We were talking about solution chemistry, and here we're talking about simple conversions and how to do some of these conversions. Okay, so a packet of artificial sweetener contains 40 milligrams of saccharin shown above. How many saccharin molecules are in a 40 milligram sample? Okay, so we want to know about molecules. How am I going to figure this out? Okay, so we're looking for how many molecules. What do I need to know to be able to go from grams to molecules? Well, I need to know the grams per molecule. I need to know the mass of that thing. How am I going to figure that out? Go to my periodic table. I'm going to have to count everything here. Okay? What are the elements that are in this compound? Carbon, hydrogen, oxygen, nitrogen, sulfur. Okay? So, 1, 2, 3, 4, 5, 6, 7 carbons. Okay? And if you disagree with me, please tell me, because it's possible I count it wrong. So, 7 carbons there. Okay? Hydrogens. 1, 2, 3, 4, 5. 5 hydrogens. 1, 2, 3 oxygens. Nitrogens, I only see 1. And sulfurs, I only see 1. Okay? Does everybody feel like that's correct? We're okay with that? Okay. So first we're going to say for carbon 12.011 times 12. What is that? Or sorry, 7 times 7. 12.011 times 7. What do you get? Who can do that for me?
84.077.
Okay. 84.077. I guess we'll just say this is 5. Okay. 16 times 3 for oxygen. 48. And then we have nitrogen is 14. And sulfur is 32. Okay. So we add those all together. What do we get? (84 plus 5 plus 48 plus 14 plus 32). What are you going to come out with?
183.077.
Okay, we'll just keep it at 183. 183 is the mass of this molecule. Okay, so 183 grams. And I'm starting with 40 milligrams, excuse me. What's wrong? Okay, so I need to convert my milligrams to grams, so 40 milligrams. Okay, and we're going to go to the grams from the milligrams. Okay, and after I do that, then I can convert the grams to the molecules. All right. So how many grams are in a milligram, or how many milligrams are in a gram? 1,000 what? 1,000 milligrams in 1 gram. Okay? So that's my first conversion. You should be familiar with milli. Okay? That's one we're going to use a whole lot in here. What number goes on top here by molecules for this conversion? 6.022 times 10 to the 23rd. So whenever I have a conversion factor and molecules or atoms or whatever, something really, really, really tiny like that, molecules or atoms or anything like that, I use this number, 6.022 times 10 to the 23rd, for its mass or by its moles. If it's moles, moles are always 1. If it's grams, grams is always figured out from the periodic table. Okay, the gram mass per mole. Okay, so this is how I'm going to set this up. So, okay, so what's the answer here for this first one? So 40 times 1 times 6.022 divided by 1,000 divided by 183. 1.316.
Yeah. Times 10 to the 28.
Okay, that's better. Um,
28. Not 28.
I was going to say 28. I don't think it can be over 23. 20th. Right?
Yeah.
Okay. Okay, 1.316 times 10 to the 20th molecules. Okay? And that's how we're going to get there. That's how many molecules we have. Okay? Now, here's a further question. How many carbon atoms are in a 40 milligram sample? I've already done most of the work to answer this question, but now it wants to know carbon atoms. So does anybody see a relationship that's going, or a conversion that would help me determine the number of carbon atoms here? What's that?
84.
The mass?
Yeah, the mass.
Okay. We don't, no, not by mass. We're not going to do it by mass. I guess there is a way we could do it, but it's not going to help. We'd have to start kind of over.
Does it have to do with the moles?
Nope, not with the moles. Let me set up. Yeah, it is a ratio of what?
Ratio of carbon atoms to the rest of the
Uh-huh. Which is what?
7 to 8, 10, 7 to
You're on the right track. Let me do this, okay? Molecule. So we're starting with 1.316 times 10 to the 20th molecules. Okay? And we want to go to carbon atoms from the molecules. What's the relationship? How many carbon atoms are there in a molecule?
7.
There you go. 7 carbons in one molecule. Got it? So we already know the molecules. Now I just need to know how many carbons are in every one molecule. So that number times 7, basically. That's all I have to do. So what is that? (1.316) times 10 to the 20th times 7.
9.21 times 10 to the 20.
Okay, good. So that's how many carbon atoms are in this many molecules, which there's this many molecules in that 40 milligram sample. Okay,
Okay, yeah, I get it.
got it?
Yeah, because I mean, yeah, that's pretty much however big that number is. There's 7 atoms in every, there's 7 carbon atoms in every one of those molecules.
Exactly.
Okay.
So this is one of them. Okay? And there's 7 carbons in it, right? So if I want to know the total number of carbon atoms in 40 milligrams, I figure out the molecules in those milligrams, and then I can set up this relationship, this ratio. There's 7 carbons for every one of those molecules, okay? And I've created this conversion factor to allow me to determine the number of carbon atoms in that 40 milligram sample. Okay? So you'll see questions like that, like how many, if you have this compound, how many atoms of oxygen or nitrogen or whatever are in that compound. Okay? So that's something that you need to be familiar with how to do. And it's simply by looking at that relationship. How many carbons are there for one molecule? There's 7 for every one. How many nitrogens are there for every one of these molecules?
Just whatever's there. It's just
1.
one.
So this would be the answer. Okay? Because it would be 1 to 1. Hydrogen was 5. So if it was asking me how many hydrogens are in this, then I put that as a 5 there. 5 hydrogen atoms for every one molecule. Okay? All right, now let's talk about percent composition. This kind of relates to what we were just talking about even. Okay? Percent composition allows us to identify the relative amounts of elements by mass in a compound. Okay? It allows us to determine the empirical formula of an unknown compound. So if we using the percent compositions of something, so they tell us you have this much percent carbon, this much percent hydrogen, this much percent oxygen in your compound, then you can figure out an empirical formula from that. And from that empirical formula, you could try to identify what that compound is. Okay? It helps us see that the masses of a compound is not determined by the amounts of individuals, but by the quantities and masses. Okay? If there's a lot of hydrogens in a compound, that's going to be a really light compound. So it might seem like it's a really big molecule, but because there's tons of hydrogens in it, you're like, oh, well, that's really light because hydrogens don't weigh anything but 1. Whereas if you have a whole bunch of these heavier elements like sulfur or chlorine, you might not think of it as a really big molecule, but it's really heavy because it has those heavier elements in it. Okay? And it kind of helps us see that and perceive that. Okay, so here we have the analysis of a 10-gram sample of a gas. It contains 2.5 grams of hydrogen and 7.5 grams of carbon. The percent composition would be calculated to be 25% hydrogen and 75% carbon. Okay? So this adds up to 10, well, it's a 10-gram sample, right? So you can easily see that, right? So we have 2.5 grams of hydrogen in a 10-gram sample, okay? And we have 7.5 grams of carbon in a 10-gram sample. Times 100, times 100. So this one's going to equal 0.25, and times 100 it will be 25%. This one's going to be 0.775 times 100 will equal 75%. Okay? So 75% of this mass of 10 is carbon. 25% of this mass is hydrogen. So these percentages help us also determine these percent compositions later will help us determine these empirical formulas and things. So they'll become very useful. Okay, so here's another example. Analysis of a 12.04 gram sample of liquid nitrogen or liquid compound of carbon, hydrogen, and nitrogen shows it contains 7.34 grams of carbon, 1.85 grams of hydrogen, and 2.85 grams of nitrogen. What is the percent composition of this compound? Okay, so set those up. Set them up and find the percent composition of each of the elements in the compound. Just in the same way we did it just in the last question. So percent is always the part over the whole times 100. Okay, so let's see if you're doing it correctly. So we have 7.34 grams of carbon over the 12.04 grams of the entire sample times 100. 1.85 grams of hydrogen divided by 12.04 grams of the entire sample times 100. And you have 2.85 grams of nitrogen over 12.04 grams of the entire sample times 100. Okay? So what is the percent composition of carbon in the sample?
16.96.
Okay, what is the percent composition of hydrogen?
13.36.
Say 15? I can't hear you very well.
15.36.
15.36. Okay, and of nitrogen?
23.67.
Okay, now add those three numbers together. What do you get?
99.99.
Okay, so you get 100%. So you need, that's one of the things you need to make sure that your percentages are adding to. Okay, is 100%. They're adding up to 100%. 99.99 is 100%. Okay, you guys like to really get it right on the exact number, but it's not always going to be exactly. It could be 100.01 or whatever, or 99.9. That's good enough. Okay, but you guys still worry about that. Oh, wait, I did something wrong. No, that's good enough. That's close enough. Okay, you did it right. Okay, so now how do we do it from just the if they gave us the formula mass, what should be the percent composition of the compounds or the elements in that formula? Okay, so we're going to find the mass of the entire compound, and then we're going to determine the mass of each individual element, and then calculate the percent by mass of the elements in the compound. Okay, so here's an example of how we would do that. Aspirin is a compound with a molecular formula of C9H8O4. So that's our molecular formula. What is the percent composition of carbon, of hydrogen, and of oxygen in the compound? Okay, so first I have my list of C9H8O4. C9 weighs 108.09. Is everybody okay with how I got that? 12 times 9. Okay. H8, 1.00794 times 8, and I get 8.064. 16 times 4, and I get 64. I add those together, and I get 180.09. That's how much that thing weighs. Okay, it weighs 0.09 grams for every mole. But they want to know the percent composition of everything in there. So what is the percent composition of carbon? Well, carbon had a mass of 108.09, right, in the compound? So I take that and I divide it by the total mass, which is 180.09, times 100. For hydrogen, same thing, 8.064 divided by 180.09 times 100. 64 divided by 180.09 times 100. These are the percentages. If I add those together, I get 100%. Okay? That's how I'm going to determine the percent composition of a single element in a compound. You simply find the total mass and then divide all the individual masses by the total mass times 100, and that'll be your percent of the elements in the compound. What is the mass percentage of iron in the compound Fe2O3? Okay, let me rewrite that so you can, like that, Fe2O3. Okay, what is the mass percentage of iron in the compound? Okay, so how are we going to figure it out? Okay, so we have Fe2, we have O3. Fe2 has a mass of what?
111.69.
Is that what you said?
Yeah.
Okay, O3 has a mass of
48.
48. Okay, those two things together?
659.
Okay, so this divided by 159.694, this divided by 159.694. Oh, well, you don't have to do it for that one because we're not figuring that one out. Times 100. And is that how you did it?
Yeah.
What'd you get?
It's like 69.9, but just running it off the side.
Okay, equals 70%.
You're okay with this running it off? Or?
If it's a multiple choice question, then it's fine. And that's what it's going to be. I mean, if it's fill in the blank, then rounding it a little bit is not even going to affect it because it's going to find it's just going to find your answer within a range. So it'll be okay. All right? Good. So that's how we do this percent composition. Now, this is the more practical area of this, as determining the empirical formula. Okay? So determining the empirical formula, there's a process. And that process is that determine the percentage of each element in a sample of a pure compound. So you probably use a machine to do that, like a gas chromatography, or you could use maybe a mass spec. Okay? And they would tell you the percentages of the the different elements in the compound. All right. Convert the percentages to masses. Convert the masses to moles, and then find the ratio in moles by dividing the mole amounts by the smallest quantity. Okay. So here we're finding the masses of A, the mass of X, the moles of A, the moles of X, and then you're dividing by the lowest number of moles to find the ratio of them to each other. Okay, because they are together, and so you want to find those ratios, and you're going to determine those ratios to whole numbers. Okay, so if one of the ratios comes out to be 1.5, then you multiply everything by 2 to get rid of that half. If one of them comes out to be 1.25, then you multiply everything by 4 to get rid of that quarter. Okay? And then we'll end up with an empirical formula. So let's look at an example here. A sample of black mineral hematite, an oxide of iron found in many iron ores, contains 34.97 grams of iron and 15.03 grams of oxygen. What is the empirical formula? So we want to find this empirical formula. So we have Fe iron equals 34.97 grams of the iron, and we have oxygen, which equals 15.03 grams of oxygen. Okay, and so this is within a sample of this. Okay, so this isn't in percentages, so they kind of helped us out a little bit. They just gave it to us in grams. That means we can convert directly to the moles from here, grams to moles. So we're going to find out how many moles of iron that is and how many moles of oxygen that is. So we say grams to moles from the grams, grams to moles from the grams. Okay, so for iron, what is the relationship here? What is the ratio of the conversion factor that I'm using?
55.8.
Okay, what goes on top first?
6.022.
No, this is moles, not molecules. Don't get those confused. Molecules are like atoms. And atoms and molecules, you'll use 6.022 times 10 to the 23rd. Moles, every 1 mole equals 6.022 times 10 to the 23rd atoms or molecules. When I come here, this number is 55.847 grams for every 1 mole. Now, if this, instead of being, if it was grams per molecules or grams per atoms, then I would use that number. But it's grams per mole. Moles are always the number 1 for moles. You always use the number 1. Okay? 1. 1. Okay, what number goes on the bottom for grams?
55.8%.
Good. Okay, and for oxygen?
16.
We'll just say 16. Okay? All right, so 34.97 divided by 55.847. What do I get? Say it louder.
0.66.
Okay? 0. Point what?
19.
Okay, these are in moles. 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 So the first step is you need to convert your grams to moles. Okay? Now that they're in moles, I have to find the ratio. The ratio between them. How many irons for how many oxygens? And the way I do that is I take the one that has the least number of moles, and I use that to divide it by everything else. So which one has the least number of moles?
Iron.
Okay, so I'm going to divide iron by itself, which will give it what? 1. So I have 1 mole of iron. How many moles of oxygen? 0.626. What does that equal to?
1.50059.
Okay, so about 1.5. So I have 1.5, right? So this is my formula as I have it right now. I have FeO 1.5. Okay, so that can't be the formula because I can't have a half. So what do I do to get rid of that half? No, don't round it. Multiply everything by what? 2 to get rid of the half. Okay, so what's my formula now? Okay, that's my formula. We multiplied this whole thing by 2 so that we could find the actual formula, empirical formula here. This is my empirical formula, Fe2O3.
That's still not that thing called balancing.
Say it again?
Balancing or equation.
No, this is not balancing. Balancing will be you'll have an actual formula, a chemical reaction, and you'll have to make sure they're the same on each side of the elements. This is simply determining the amount of everything in the formula. If we have these amounts of iron and oxygen to start with. Okay? All right, so. All right, now if it's a molecular formula, so that's how I will determine it if it's the empirical formula of an ionic compound like iron 3 oxide there. Okay? But if it's a molecular formula, then there's a little more work. You do everything else the same. You do all the beginning stuff exactly the same, but then there will be one extra step at the end that you have to do to find the actual molecular formula. Because what we just did finds the empirical formula, which for ionic compounds is great because they're always in their empirical formula. But if it's a molecule, the molecular formula is not always in its empirical formula. Okay? So look at this. This CH2O is in the empirical formula of glucose, which is C6H12O6. So this is what I would determine CH2O from my data. And then I would have to figure out how much I need to multiply that by to get the actual formula of C6H12O6. Okay? To find the molecular formula. So that's just that one extra step at the end. I do everything else the same, find the empirical formula, and then at the end, I have to make a determination to understand how much I would need to multiply it by to find the actual formula. Okay, and that's what this is. Divide the molecular mass by the empirical mass. So here I would find the empirical mass. Okay, so C6H12O6 is 180 grams. Okay, it's 180 grams. CH2O, so C12H2O, 16, 2, okay, is more like 30 grams. Okay? So this is the empirical mass. This is the molecular mass. So the molecular mass goes on top, divided by the empirical mass, which is 30. And then I would find out, so 180, somebody take 180 divided by 30. I did it right. It's 6, right? So that's how I know to multiply this whole thing by 6. Because that's the difference in the masses there. Yes? Okay, so if I actually take it as C6H12O6, 12 times 6, H12, and 6 times 16, add that together, it's going to be 180. So that's, but most of the time you don't know what that is. You don't know this formula. And so they say, we took a 180 gram sample. This thing weighs 180 grams. Okay? And then you find the molecular empirical formula of it, and you'll know what the mass is. Okay? So they'll say the molecular mass of this thing is this, etc. And then you take the empirical mass and you divide it by the molecular mass to find out how much I need to multiply it by. I need to multiply it by 6. Okay? Because that's the difference in those masses in the ratio. Okay? So let's see, here's an example. So we have nicotine. Contains 74.02% carbon, 8.710% hydrogen, and 17.27% nitrogen. If 40.57 grams of nicotine contains 0.2500 moles of nicotine, what is the molecular formula? So that last part there we're going to leave for the end. Let's go ahead and find out the empirical formula. We have to find the empirical formula, then we'll figure out what the molecular formula is. Okay? So let's start out. We have carbon, hydrogen, nitrogen. Now these are not in gram amounts this time. They're in percentages. But guess what? You're going to do everything the same. Because what I am considering here is that this is simply out of 100 grams. It's 100 grams. Let's just say it's a 100 gram sample. Okay, that's what we're going to assume. And we're going to say that, therefore, it's 74.02 grams. It's 8.710 grams. And it's 17.27 grams in every 100 gram sample. Okay? So you don't have to do anything different. If they give you the percentages or the masses, it's the same. You're going to do the same process. So we're going to go from grams to moles, from grams to moles, and from the grams to the moles. Okay? So what number goes?
You gotta.
Jeez. Guys. Alright, going too fast. Moles to the moles. I even kept saying it right and I'm doing it wrong. Okay, so what number goes on top? 1. Because it's the moles, right? What number goes on the bottom?
16. 1.
Okay, so 12.011 for carbon. Hydrogen, 1.00794, or you could just say 1. Nitrogen, 1 for every 14 point, etc. 0067, 14. Okay? Those aren't going to round enough to make it significant to have these. You could just say 12, 1, and 14 there. That would be fine. Okay, so what is it? Carbon, 74.02 divided by 12.
6.1683.
Okay, hydrogen, 8.710 divided by 1. It's like the same, right, guys? Okay. Okay, these are all moles. 17.27 divided by 14.
1.2335.
Okay. Now what do I do? Okay, which one's the smallest? Nitrogen. So divide everything by the moles of nitrogen. Divided by 1.2335 moles. Divided by 1.2335 moles. divided by 1.2335 moles. Okay, what do I find?
5.00061.
Okay,
And then 7.0612.
okay, and this is 1. Good. So this is good. Everything turns out pretty good. Okay, so I don't need to multiply the final thing by anything because I have whole numbers here. So C5, H7, N. Okay? So this is my empirical formula. This is my empirical formula for this compound. Okay? Now, I need to determine the molecular formula. The molecular formula should be determined from the molecular mass. And the molecular masses are like these ones over here. Okay? The gram mass is over here. So for phosphorus, for example, it's 30.97376 grams per what? Mole. Now they didn't tell me the actual mass of this thing. They just said you had 40.57 grams of it. They didn't tell me the molecular mass though. So I need to find the grams per mole. That will be my molecular mass. They did tell me the moles. So I need to find the molecular mass by taking 40.57 grams of this and dividing it by 0.2500 moles to find the grams per mole. What is it?
162.28.
Okay, 162.28 grams per mole. That's my molecular mass. Okay? So, this right here, C5H7N, is my empirical formula. I need to find the mass of that. C5H7N. What's 12 times 5? Oops. Okay, is that what you guys are getting? 81?
Yep.
Okay, so take 162.28 and divide it by 81. What are you going to get? What's that? 2, right? You get 2. So we're going to take this C5H7N and we're going to multiply everything by 2. C10, H14, N2 is the molecular formula for this compound. Okay? Because this divided by 81 equals 2. And so I need to multiply this by 2. Everything by 2. C10H14 N2. That's my molecular formula. Oh, yeah, it's up in the question right here. You have 40.57 grams sample of nicotine, and it contains this many moles of nicotine.
Okay.
So that's how I found the molecular mass. Okay. Okay, any questions so far about that?
Why do we divide the 162 by 81?
Okay, because this is the molecular mass, okay, and 81 is the mass of the empirical formula. And so the difference between those is this. This divided by that. It's a factor of 2. That's the difference between them. So that means that if I multiply that by 2, it's going to equal 162.2. So if I find the mass of this right here, C10, H14, and 2, it's going to be 162.
Okay.
Because it's a factor difference of 2 there. Okay? So to find that number 2, we have to divide the molecular formula by the empirical formula to determine how many I need to multiply this empirical formula by to make it the molecular formula. Okay? Okay, we're okay with that? Any more questions? All right, let's go. Okay. So here we see a cup of coffee and they're putting sugar into it, right? So the amount of sugar, I can add sugar to that thing all day, right? And it's just going to keep dissolving, and more of it's going to dissolve, and then more of it's going to dissolve, and more of it's going to dissolve, okay? And as I'm adding more and more sugar, what's happening to the concentration of the sugar in the solution? It's increasing, right? So we're going to try to understand how to determine these concentrations in their ratios of how much sugar there is per so much of solution, okay? But we're going to try to do it in molar quantities, okay? So how many moles instead of grams? So whenever we say moles, we're talking about the amount, and that's kind of like the mass of it, the moles. How much there is of that thing per this amount of it, okay? So we're going to look at this in ratios of concentration in molar ratios. And to do that, we use this equation for molarity, okay? Molarity is the well, let's put a space there, is the relationship of the moles of a solute in a volume of solution, okay? It is calculated as the moles per liter. That's important. Per liter. It has to be in liters volume. If it's in milliliters, you are going to have to change it to liters because it can't be in milliliter volumes. It can only be in liter volumes. So the solution is made up of the solute and solvent volumes together. So here is the molarity. The moles of the solute over the liters of solution. Moles per liter. This is the equation. Okay? And from this equation, I'm going to be able to identify the concentration or describe the concentration of a solute in that solution. Yes?
With this equation, is liter going to be universal? Like, I can't use a different volume, I can convert it to liter?
Yes, that's correct. With this equation, it always has to be in liters. Now, that doesn't mean if you have 0.5 moles of something and you have 0.5 liters of something and you pour them together, then that doesn't make a 1 molar solution necessarily. Because what I'm not considering is that the volume will change once I pour those two things together. Okay? So when I pour them together, the volume changes. And now I have to figure out what the new volume is of the entire solution. Because this is liters of solution, not liters of the solvent. Okay? So make sure you have that distinction. It's not going to be very often that you'll have to make that distinction. But it's possible you would need to. So make sure you understand that. This is of the entire solution. The moles of the solute, the individual thing that's dissolved in the solution, and the liters of the entire solution, not the liters of the solvent. Because once I put them together, the volume can change. That's the volume I use. The new volume, the final volume of this solution. Okay? Okay, so A 355 milliliter soft drink sample contains 0.133 moles of sucrose. What is the molar concentration of sucrose in the beverage? So, our equation is molarity equals the moles per the liters. This is a very straightforward question. They want me to find the concentration, the molarity. Molarity is the concentration. They told me what the moles are. The moles are 0.133 moles. Now, they didn't tell me the liters, but they did give me the milliliters. Okay? So what are the liters here? Okay? So if you can't look at that and determine that's 0.355 liters, then set up the conversion. 355 milliliters in a liter from the milliliters. So there's 1 liter, there's 1,000 milliliters. 355 divided by 1,000 is in fact 0.355 liters. Okay? So if I had 1,000 milliliters, it would be 1 liter, right? So if I have 355 milliliters, that's 0.355 liters. If I have 35 milliliters, that's 0.035 liters. Okay? So that's kind of how that's going to work. And I would say most often you would see it in hundreds of milliliters. And so just put the decimal place in the front of it. And that's your liters. Okay? This is going to be very commonplace of the kind of thing we're going to be doing between liters and milliliters, or milligrams and grams, or kilograms and grams, okay, etc. So make sure you have that milli conversion figured out. So 0.133 divided by 3.55, what is it? What's the molar concentration here? I'm sorry, say it louder. 0.374 molar. So that's my molar concentration. What does that actually mean? If you see something that is 0.374 molar, this is what you know. This is equal to 0.374 moles in every 1 liter. Every 1 liter of that solution has 0.374 moles in it. Has 0.374 moles in it. So what if you had half of a liter? How many moles would be in half a liter? Divided in half, right? And that would be how many moles are in half of that liter. How many moles are in a quarter of that liter? Divide by 4. And it would be how many are in a quarter of it. Okay? So this is what this means. Okay? And if I was going to prepare a 0.374 molar solution in 1 liter, how many moles would I need? 0.374 moles. And I would need to dissolve it into 1 liter, and I would make a 0.374 molar solution of it. If I dissolved 1 mole of it into 1 liter, I would have what molar concentration? I would have a 1 molar concentration. Okay? So if I want to make a solution that is 1 molar, I simply need to dissolve 1 mole of it into 1 liter. And it's a 1 molar solution. Okay? All right. So, how much sugar in moles is contained in a modest sip, approximately 10 milliliters, of the soft drink from this example above? So, what am I solving for? I want to know the moles. I'm solving for the moles. Well, if molarity equals moles per the liters. What does moles equal?
6.022.
No. I mean from this equation. Rearrange it so that you find the moles. Yes. Bring the liters up. Molarity times the liters, right? So if I want to find the moles in a molar solution and I know the volume of that, I can do that. Okay? I simply need to know the molarity. The moles equals the molarity. What is the molarity that we just determined? What was it? 374 molar times. Okay, this is I need to put the milliliters into liters. 0.01 liters. Now, for units, if I show the molarity units, it's moles per liter, and my liters cancel, and I'm left with moles. Okay? So, my moles are equal to what?
3.74 times
3.74.
times 10 to the negative 3.
Negative 3?
Yeah.
Moles. Okay, is that what everybody's getting? Okay? So 3.74 times 10 negative 3 moles. That's how many moles are in a sip. I take a sip of that. It's about 10 milliliters. And there's 3.74 times 10 negative 3 moles in that sip. Okay? Whereas in 1 liter, there would be 3.374 moles of it. Okay, so moles from molarity and volume. That's how I'd find the moles from having the molarity and the volume relationships. Let's try another example. Distilled white vinegar is a solution of acetic acid. And there's the molecular formula. Okay? A 0.5 liter vinegar sample, so 500 milliliter sample, contains 25.2 grams of acetic acid. What is the concentration of the acetic acid solution in units of molarity? Well, molarity equals what? Moles over liters. Do I have the moles? They didn't tell me the exact moles. Can I determine the moles? Yes, I can. Because they told me what? They told me the grams of vinegar or of acetic acid. Okay? So, I'm going to have to set up a conversion. 25.2 grams of acetic acid, and I'm going to convert that to the moles of acetic acid from the grams of acetic acid. What number goes on top in this conversion? 1. The number 1 for the moles. How am I going to find the number that goes on the bottom? That's right. I have to find the molecular mass of acetic acid. So we have C2H4O2. Okay? So we have 2 carbons here. We have 4 hydrogens. And we have 2 oxygens. Okay? I'm sorry? 3 hydrogens here and 1 hydrogen here. So I just combined them into H4.
Is there a reason why it's
Mm-hmm. There is. Because the actual, it would be CHHH COOH. So that's why they arrange it that way. And this is the acidic hydrogen right here, the one that comes on and off. Okay. All right. So here we have 1 mole for every 60 grams. So 25.2 divided by 60. What do I find? Say it again. Moles. 0.42 moles. Okay, so those are my moles. Now I have my moles. Do I have my liters? Yeah, they even put it in liters, didn't they? So instead of saying 500 milliliters, they said 0.5 liters. So 0.42 moles divided by 0.5 liters. What's my molarity here?
1.68.
That doesn't seem. Is it 168?
0.84.
Okay, that sounds more. 0.8. That seemed more right. Is that what everybody's getting? Is there a consensus on that? Oh, did I write it wrong? 0.84. Okay, good. And that's good because that's actually that's really what the vinegar you buy at the grocery store. It's about 0.84 molar solution. Okay? All right. Calculate the molarity of 6.52 grams of cobalt 2 chloride, excuse me. Wow, they even gave you the mass. You don't have to calculate the molecular mass there. 128.9 grams per mole. Dissolved in an aqueous solution with a total volume of 75 milliliters. Okay, go ahead, do it. Okay, so what equation am I using? What am I solving for? Molarity. And molarity equals what? Moles over liters. Did they give me the moles?
Yes.
Okay, they didn't directly give me the moles.
Conversion.
I have to convert the grams to moles. Okay, so that would be 6.52 grams of cobalt chloride converted to the moles from the grams. The molecular mass is 128.9 for every 1 mole. What is that? What did you guys find? Say it again. Okay. So these are the moles. Okay. They didn't give me the liters directly. They gave me the milliliters, but I can easily convert the milliliters to liters. Okay. So this is 0.05 moles divided by how many liters? 0.075 liters. So 0.5 divided by 0.05 divided by 0.075. What's the molarity? I'm sorry. What is it again?
0.674.
Okay. 0.674 molar. Great. Great job. Okay. Okay. We'll do this one next time. All right.